last question, right?
Yeah.
Okay.
Sure, yeah.
So
Yeah.
I will request all the students. You can ask anytime any question to
Yeah,
Subhash. So yeah.
I'm also
Okay.
going to say the same thing,
Yeah.
Yeah.
Okay.
Yeah,
Okay.
yeah.
Thank you.
Okay.
Okay.
Yeah, so first I would like to thank the Alice India Committee for inviting me for this presentation. So today I'll mostly talk about this what's called this instrumental effects and the unfolding, which is also part of my PhD thesis that I worked on in Alice. Like we worked on a detector called the Photon Multiplicity Detector. We measured the multiplicity of the photons and we applied this unfolding method. So I'll basically show some examples using this PMD or this Photon Multiplicity Detector. So I divide this talk in or this lecture in like 3 parts. So first I will start with a very brief introduction. Then I'll discuss about something on the instrumental effects, and then I'll show some of the unfolding methods that's used in this heavy-ion collisions or in high-energy collisions. So let me start with an introduction. So we all have encountered this kind of problems that I showed here in the picture. Like we all have a smartphone in our hand, and while we are driving or something, we took a picture and it somewhat get blurred. Now, so this is like an human error that can happen in any instrument. And there are algorithms with which you can recover back the real image, like what is shown here on this right-hand side, plot, right? So, there are also other ways you can do it, like if we go to like in physics, like in astrophysics, we also have a similar kind of problem. Like when we take picture of the galaxies, like shown here on this top left side, this is a picture of this galaxy NGC 1068 taken with a camera or a telescope which has a very poor resolution. And the bottom one is the one where we have a better resolution. And one on the right here, this shows on the top right shows here that is deconvoluted, like one tries to recover back the picture using some algorithms. So this general method of so why we have such poor resolution is because of the detector resolution. So the detector resolution that causes the smearing, and because of such smearing, we are not able to get back the real distribution, which is shown here on this bottom picture. So this method where we try to get back the original distribution from the smear distribution is known as a deconvolution. So this is a general a statistical phenomena which happens in many areas of science, and there are techniques to either correct for it or get back this original distribution, which we'll talk about later. Okay. So let me first show you this Alice detector, which is like the main detector and one of the purpose of this main meeting. So in Alice also we do the same thing. We also, it's like taking pictures. So like we reconstruct particles. And there also we have these several kind of instrumental effects. And because of those instrumental effects, we do not have what's called the real or the true measurement. So I would like to point here one detector that is called the PMD or Photon Multiplicity Detector, which is like an Indian detector, which is installed somewhere here at the forward rapidity in Alice. And okay, so let's now see. So this slide, basically, I am showing you the different position, acceptance, and different technology used for different subcomponents of the detector that we have in Alice. Okay, so this just gives you basically an overview of what we have in Alice detector. So then let me briefly talk about the PMD or the Photon Multiplicity Detector. Why I'm talking about PMD? Because I'll be using several examples of the unfolding and detector instrumental effects using this detector. So this PMD has 3 planes. One is called the pre-shower. Then there is one late converter, and the CPV is known as the charge particle veto. It has 24 modules in each plane with cells in total of like 4,608. The PMD is located at around eta 2.3 to 3.9. Somewhere here you can see in this picture the real picture of the PMD, which is like 3.67 meters away from the center of the TPC. So what we measure in the PMD is basically the photons or the inclusive photons. And in this PMD, this is like a gas detector. And what happens is like, so let me now tell you briefly about the basic principle of the PMD, how it works, because we'll be also using this kind of information later in the discussions. So PMD has 3 planes, as I said here, the P-shower, the lead plane, and this charge particle veto. So let's consider this is our CPV, and then we have, let's say, a lead converter here, and then we have a pre-shower plane. So, for example, when a photons, or for example, when a charge particle hits our detector, what will happen? It will pass through the CPV. It will give one hit in the CPV. Then it will pass through this lead converter and through the PMD. But when a photon will pass through the PMD, what will happen? It will produce some showering inside the PMD, and because of that showering, what will happen? It will affect more than one cell. So by using certain cuts or thresholds on this number of energy that is deposited by the photons or the single charge particles, so the single charge particle will affect only one cell, it's most likely, whereas these photons on an average will affect the cells, which is, let's say, more than 2. In terms of ADC, the charge particle will also deposit less energy, and the photon will deposit more energy. So depending on this criteria, we can distinguish between the photons and the charge particles in the PMD in principle. Okay. So in PMD, we can also measure at which point the particle hits the detector. For example, if it hits here, we know the X and Y position in the detector, which is called this cluster X, Y, and Z. And from this X, Y, Z composition, I mean these numbers, we can calculate the eta, the pseudo rapidity, phi, these kind of informations. Okay. So having said that, let me now go to the second part of my presentation, which is about these instrumental effects. What kind of instrumental effects we can expect in our experiment? So so do you have any question up to this time?
Hello.
Okay.
Sir.
Yeah.
Yes. So as you mentioned, the photon has produced more light energy than the charge particle. What is the reason behind it?
Yeah. So when so there is a lead converter in between the PMD, right? So there is 2 planes. One plane is CPV, and there is one plane is pre-shower. So when photon traverses through the PMD, when it hits this lead converter, in the lead converter, the photon will interact with the lead and produce the shower, right?
Yes.
Whereas when a charge particle passes through the PMD, it will not produce that shower. So because of that showering, the photon will affect more than one cells, whereas the charge particle will affect likely one cell. So using this discrimination, we can like discriminate between the photons and the charge particles.
Okay. Thank you.
Okay. Is there any other questions up to this part? Okay. So if not, so let's go to the second part of this presentation, which is about the, yeah.
So what are those showering? What are those showering you are talking about? Shower.
Shower means your photon will so your photon will interact with this lead particle and will produce charge particles like your pi 0.
Okay, sir.
Okay, so so let me now go to this second part, which is about this instrumental effects. So the first thing is we in our experiment, what's important is about this acceptance. So I already showed in this slide that you can see the list of the various detectors, and they have various acceptances in eta. For example, the TPC, it has acceptance plus minus 0.9 in Alice. PMD, we have an acceptance between 2.3 to 3.9. But it can also happen in an experiment that some of our detector modules are not working properly or are not present in the real data. For example, this plot shows here the hits in the pre-shower plane of the PMD. So you can see, like in this module number 10, this module is not working in one of the data. For example, when we are taking data in PP collisions at 900 GeV. So what it happens, we lose some information or we lose some acceptance. So in reality, what happens if you have 100 photons hits on your PMD, or the 100 photons are generated in a PP collisions, and then it hit on the PMD, because of these acceptance issues, we'll not be able to detect all the 100 photons. For example, we'll be able to detect 75. So we have to correct our measured photons with this fraction, which we called an acceptance correction or an acceptance function. So here I'm showing such value of such acceptance correction for this PP 900 GeV data. You can see, like this point here, this is very close to the beam rapidity. You can see the density of the particle is more. So the acceptance close to the beam rapidity is better. And you can see also here, when we look at the higher rapidity, our acceptance is very good. It's close to 95%. Whereas as we go towards on the other side, on the lower side of the rapidity, we have several cells that are not present. For example, this cell number 10, there's some part of the missing of this 17, number 4. So we lose some particles. So if we measure, for example, 80 particles, we have to divide by this factor like 0.75 to correct for this acceptance effect, okay? Okay, so after this acceptance part, then there is another part is also important, that is called the efficiency. So in general, efficiency, we defined it as like a measured event by the true events. Like even if you have in your detector have 100% acceptance, there is no dead cell, there is no gap between the sectors, for example, in the PMD, even after that, you might lose some particles. So that is defined by this efficiency part. So if we take an example of PMD, how do we define this efficiency? We can define it by this N gamma detected by this N gamma incident. So let's define what these two are. So this efficiency we can calculate using like a simulation. Like we have in Alice, we can generate some events using Pythia, and then this Pythia can generate some photons, and then those photons can pass through the Geon or the PMD that is installed, or the PMD. That's for example, okay? And then we have something that is we detect in our detector. So the ratio between this detected part and this incident part is called the efficiency. So this figure here shows you about this how this efficiency in the PMD looks like, okay? So the x-axis is actually the various cuts or threshold that I talked about. Like when we have no cut means we are not discriminating, we're not applying any discrimination cut, and we can see our efficiency is very high. When we are making the cut stricter and stricter, that means we're losing the particles only in our numerator, but our denominator remains the same. Then you lose your efficiency. But you can lose your efficiency, but you can, if you calculate the purity of the samples, you can see if you apply much more stricter cut, your purity will also increase. So this is like a competition between the efficiency and purity, and in real experiment, you have to choose whichever is best or the suitable for you. So next, another thing is about the efficiency. So this is about the efficiency, for example, when you detect the number of charged particles. We also have another efficiency. This is called the reconstruction efficiency, which is for example, used in spectra analysis. Then also what we do, we have in ALICE, we have this kind of event generator for PP collisions. We can use Pythia. For heavy ions, we can use, for example, Hygiene. Then we pass through the GIA, and then we reconstruct back in the simulation. Then we take the ratio between the reconstruct and the input. And this is what gives us the efficiency. For example, if we give a flat PT distribution as an input here, and after this reconstruction, what we are getting is something like this. So this is like our efficiency. Let's say this is 75%. Okay, so this is what we also need to correct for this efficiency when we are measuring our, like for example, PT spectra, or in our previous examples when we measure the number of photons or number of charged particles, etc. Okay, so yeah. So the next thing what I want to talk about, another thing is also very important for the unfolding problem, is the resolution. So we all have the idea of some basic idea of resolution, like when we use different mobile phones or different cameras, they have different resolutions depending on the pixel size, right? So the basic definition of this energy resolution is the ability to distinguish the two close-lying energies. For example, if we have two signals, whether or not we can distinguish between those two signals, that is defined by this energy resolution. So usually we represent it by this full width at half maxima, or FWHM. So can anyone tell me, like in ALICE, what are the detectors that we can measure the energy of charged particles, for example, or photons?
Calorimeters.
Yeah, that's good. Yeah, in calorimeter we can also measure the energy, and the typical energy resolution in the calorimeter is of the order of, it's not an exact number, but of the order of maybe 10% or 10 to 15% of that order. One can measure the resolution in the calorimeter. So similarly, we also in our experiment we also measured the momentum, and there's also some resolution associated with the momentum. And one can express this momentum resolution naively using this kind of parameterization formula, where this B is this magnetic field, L is the track length, this is the number of head rows in the TPC. One can see this resolution is mostly a linear function as a PT. It increases with PT in the high PT region, and it has a deep and up structure in this low PT region. And energy resolution can also affect our measurement. So it can cause some smearing in our measurement. So if we have momentum, let's say 5 GeV, because of this momentum resolution, we can get some kind of smearing. Okay. So there is another effect that can affect our measurement, which is called the background. It's also very important. Like here, I'm showing an example of this PMD. Like if you look into PMD, in front of PMD, there are various detectors. For example, there is V0. If you look into the real picture of the PMD, you can see here, you can see here, there are many materials in front of PMD. So the charge, so the photons or the particles that are depositing or going towards the PMD that can hit the other detectors, and that can also cause and those interactions can cause something like background in our measurement. We can also understand those backgrounds by various ways. Here I am showing one example of this eta minus eta origin or phi minus phi origin examples. So for example, if we have a collision at a vertex, and you know your PMD is at a distance of around 3.67 meters, and you can calculate the eta of each of the points. Now, if you add the materials in between, and you see how your eta deviate from that eta origin or phi origin, and you can calculate the distribution. And one can see that this kind of bump that we see here at high eta, this is because of the particle that is deflecting from the beam pipe. So we can understand this background in our experiment. Okay. So finally, let's summarize this part. So in any experimental measurements, we have various instrumental effects. For example, we talk about, we have the finite acceptance. We have this detection efficiency or the detector efficiency. We have the detector resolution. For example, we have this energy resolution. We also have the momentum resolution. And there's also the effect from the backgrounds, like different backgrounds. And these are also depending on different analyses, that background contributions can be different. So in real life, what we need to do, we need to correct for these effects. And yeah, so in the second part of my talk, I'll discuss how we'll be able to correct these experimental effects using a method that is called the unfolding. So yeah, so do you have any question or anything on this part of this presentation? Okay, so if there
hello.
is no, yeah.
Yes, hello, Swada. I want to know in the reconstruction efficiency, the input we take as the flat PT spectra. What is the reason for this? If you take any shape, what will happen to the output, like reconstruction efficiency time acceptance as function of PT?
Yeah, the flat PT we usually take because of the statistics. Like if you want to generate a particle, so usually your PT spectra is like an exponential form, right? So if you want to generate this kind of PT spectra, you need more events because the probability of finding high PT particles is less compared to the low PT. But if you use a flat PT, you'll need less number of events. So this is one of the reasons in STAR in STAR, we use this kind of flat PT as an input to get this reconstruction efficiency. But in ALICE, sometimes we also use in input, we use like Pythia or Hygiene. So Pythia, Hygiene, they also have this kind of, I don't know, it's like an exponential shape or like power law shape. So using that, you can also, you can also get the efficiency. So the main thing is about this, the statistics. Like if you have an exponential shape, you need more statistics to generate, or you need to generate more simulations. So it's like computationally more exhaustive compared to this one.
Okay. Now I am concerned about this output shape. Like if you take a different shape of input function, then one of the reason is, I agree, the statistics is important to the number events should be equal from the each PT beans. If you take the different input shape, the output efficiency time acceptance function PT, it will affect the shape, or the shape will remain shape?
That also depends on your various analysis, but one can also do this kind of reweighting. I think in ALICE, people also do this kind of, so this is like a very technical question, right? So in ALICE, people also do some kind of reweighting. So like you reweight your input spectra such that it looks like a measured spectra. And then you like weight both in your input, and also you weight in your reweight in input and output, and then you get the efficiency. So if you do the reweighting,
need to correct.
Yeah, so if you do that kind of reweighting, that mostly affect the low PT part of the spectra in this PT spectra analysis, and that affects, I think, like 5 to 10%, right? That effect is of the order of 5 to 10%. Yeah.
Okay, thank you.
Hello.
Yeah.
Sir, apart from flat PT, they also take the exponential PT distribution. So how is it different from flat PT?
I mean, these things are like related to like different analysis, as I said. Like these are very analysis specific things, like requirements. In your analysis, whether you need this kind of distribution or that kind of distributions, these are analysis specific, very analysis specific. So whether you take this flat distribution or exponential distribution, you have to you will get some efficiency. But as as was raised by Dukisham, is that if there is also a way that one can also correct for this kind of shape, like if your input distribution has a different shape than the measured one, there are ways for like reweighting one can correct for these effects.
Okay, sir. Thank you. For reconstruction of strange particles, actually people ask for the flat PT distribution and exponential PT distribution, both in star experiment.
Yeah, and if you compare the efficiency between those two, they are not very different. Maybe differ by 5% of the order of 5% or 10%. Yeah, right. Yeah. So your final efficiency will not be that different. Yes, please go ahead.
Okay, sir.
So that's like part of your.
They are due to the statistics.
Yeah, but that was done part of because of some systematic checks.
Yeah, yes, for systematic
like if you
checks.
Systematic checks. For example, if you take a instead of a flat distribution, if you take a realistic distribution, how your efficiency is changing. So that's like part of your systematics.
Yes, sir. Thank you, sir.
Okay. Any other question in this part? Okay, so if not, let me go to the second part because we have kind of a limited time. So about this, so let me now go to this unfolding method. So why we need unfolding method? That's the basic question, right? Like in experiment, we can measure and we can, for example, if we measure charge particles, we can get some number. So why we need the unfolding method? Because we need to correct for these effects and we need to get the true number or the true distribution, right? So let's first define the unfolding method. So for example, we have a true distribution. For example, there's a PP collision and we have a distribution of, for example, we have the distribution of these photons in gamma, and you have in y-axis, you have P of in gamma, right? So this distribution looks like somewhat like this, right? Now in experiment, because of the experimental effects that I talked, that I pointed out, these effects, your distribution may not be the exact true distribution. It can get smeared. It can go somewhat like this or somewhat like this. We don't know, right? So this response we can calculate in simulation by a matrix which is called the response matrix. So in simulation, we can do this response matrix. So the response matrix gives us the conditional probability that if a collision that has a true multiplicity I, then Rij gives the probability, the conditional probability that a collision with true multiplicity I is measured as an event with a multiplicity J, right? So if you want to get the true distribution, what we have to do, we have to apply the inverse of the matrix on this measured distribution, okay? So, but then there is a mathematical problem in that. This matrix inversion can cause some large fluctuation in our result. And let's try to see this via a very simple example, okay? So let's take an example like this. We have this x1 and x2. For example, let's consider this is our true distribution that's happened in our experiment, and we don't know about the true. What we do, we know only about this measured part, right? So if we want to get the true distribution, what we have to do, we have to inverse of this matrix and apply on this measured distribution. For example, we have this matrix as 1 and 2. This is our measured distribution, and we're applying this inverse of this response matrix on this measured distribution. So can anyone tell me what's the result? What will be the result of this kind of matrix inversion here? It's a very simple matrix.
1 by 0.900.
You can take some time, maybe 30 seconds, and give me the number. Okay, you can confirm if this number is whether or not this number is 1.11 and this number should be 0, this number 0.0 and 1.25. Can someone confirm these numbers? So this will apply on your 1 and 2. So is anyone doing this or
1.11, 2.5.
okay? So yeah, so you can do this kind of matrix inversion and you can get your final numbers, right? By multiplying this matrix, right? So now in second example, what we can do, we can also add the off diagonal elements. For example, we add here this 0.6 and this 1.0 over here, right? And there also you can do the matrix inversion and you can do the same calculation like I did. And if you do this, you will see that if we have these off diagonal elements in your response matrix, and if you invert that response matrix, that will cause very large oscillation. And if you can calculate the variance of the matrix, that will also be a very large. So this is like a mathematical problem. Like if you have this kind of measure distribution with a response matrix on true distribution, and if you want to get back the true distribution by simply applying this inverse of the response matrix, you will get very large oscillation in this result. You can do this simple matrix inversions and you can check. So because of this problem, this unfolding is called an ill-posed problem. Okay. So there are ways to correct for this kind of problem, and this is known as the regularization. Okay, so you can reduce these oscillations or the large variation. Yeah.
So I didn't understand what do you mean by large oscillations. What's the problem? Because we are inverting, and so what is the problem? I didn't get.
So okay. So let's take an example of this one. Okay. For example, you have a true distribution. Your true distribution have a very fine bins, for example, okay? There's a 1, 2, 3, 4, 5, 6. But your measured distribution, you doesn't have that kind of resolution. You have 2, 4, 6. So when you do the matrix inversion with this kind of matrix, this information, when you try to get back to this fine bin from this coarse bin, some information is lost. So that lost information will cause a large oscillation in your solution. You can simply take an example like this numerical example, and you can apply the response matrix, and you can see that your final solution will have very large oscillation, like very large fluctuating numbers. And if you calculate the variance, that variance will also be very large. Okay, I'll show one graphical representation in the next slides, or after a few slides. Is it clear or?
Okay, you can proceed. If I have a problem, I will let you know.
Okay. Yeah. So, what's exactly your question? I mean, maybe I didn't get your.
No, actually, you have a x1, so I have a y1, y2.
Mm-hmm.
So, and there for a given y1, y2, will the R be different? Because with what are the oscillations? So someone means we have a fixed y1, y2, that is 1 or 2, 1, 1, 2, what you showed in the previous slide. So if you go to the previous slide.
Yes. So this is a very simple example where you have only the diagonal elements. So here you have no problems, right?
You have no problem means means here, what is your problem? Like you are multiplying and you will get a number. So what is the problem here? Means just mathematically you are showing. So means what is the problem in this? You can multiply, you can get the x1, x2. And also in the next also you will get some x1, x2. So where come the oscillations are coming in these examples? So that's
yeah, these oscillations are coming from these off-diagonal terms in this inverse matrix. I can show you some example later in the slides how this oscillation will come in real case when we are applying in the real data. Okay.
Okay.
Yeah. So to reduce those oscillations, we have to apply, this is called regularization. Okay. So in unfolding, there are various ways we can do the unfolding. One of the method that is known as the chi-square minimization. So basically for chi-square, in general chi-square, we defined it as something like this, like we have I equal to 1 to n, we have an xi observations, and let's say this is the average of that, and sigma I is the error. So we take the square of this as an chi-square, right? So similarly, we can also define our chi-square like this, where the mi is your measure distribution, u is the guess distribution, and rij is your response matrix, and ei is the error on your measurement. Okay. Now, if you do this kind of unfolding, and if you try to apply this unfolding, so this example is shown here, right? So here, so you can take a response matrix, and in that response matrix in the simulation, you have a true distribution, you have a measured distribution, and you also have a response matrix. Then you can simply apply the inverse of the response matrix on this measured distribution. Then what you get is called as unfolded distribution. And if you see that this unfolded distribution have very large oscillations about, as shown here by these red lines. Okay, so this is what I'm talking about. So these things is done in simulation. For example, we have in ALICE, for example, you generate a Pythia, and in Pythia you get a photon multiplicity distribution, for example, in gamma distribution, which is the true distribution, and then you pass it through your ALICE detector or your GIA, and then you have another distribution that is called N gamma measured or N gamma detected. Then you can reconstruct a response matrix, which will be your N gamma true versus your N gamma measured. So this is like a 2D histogram. You will get something like this. Then you can apply this inverse of this response matrix on your measured distribution. If you apply them on your measured distribution, in principle, you should get back this N gamma true. But if you do this, you will see that you will not get back this N gamma true. Instead, because of this mathematical problem, you will see very large oscillation in the results. So this is what I'm talking about. Okay, so to reduce this kind of oscillation, what we do, we add this regularization term. For example, in chi-square, we can add this. There is a beta factor, which is a weight factor, with another term. This is called a regularization term or a PU term. So this in simulation, we try to optimize both this beta and this regularization. So let me go to the next slide and show you the different forms of the regularization. So this PU or this regularization term is actually an ad hoc information. For example, if my unfolded distribution is favored as a constant function, or whether it is favored as a linear function, or whether it is favored as an exponential function, we can use different form of this PU. So what it does is basically adds a constraint on your unfolded distribution, right? But you also have another term here that is called beta. So we also have to optimize this beta value. If the beta value is large, then your chi-square will also be large. If your beta is small, then it will be like under, what's called this, under regularization. I'll also show some example for this part, okay? So yeah, so let's now start again with this PMD example that we have a true distribution of photon multiplicity, for example, N gamma measured. N gamma true, we also have this N gamma measured. So in simulation, what we do, we generate the true distribution in PP collisions using PTR Fudget. We pass it through GIA, and then we get what's called the measured distribution or N gamma detected. Then we can make a two-dimensional histogram where x-axis is the true multiplicity and y-axis is the measured multiplicity. So this is our response matrix. So if you can take any slice here, for example, if you project this histogram on the y-axis, so what's the probability of getting this multiplicity true? For example, 20, you will see this distribution will look somewhat like this. So this tells you about the probability of measuring this multiplicity 20. So 20 can be measured as 20. It can also be measured at somewhat different value depending on the structure of your response matrix or the width or the dispersion of the response matrix. Okay. So let's see an example. What happens? So in simulation, in simulations, everything is like we know. Like we have a true distribution, we know our true distribution. This true distribution or these photons, they pass through your GR simulation, and then you have a measured distribution. You reconstruct a response matrix from here. What you do then, you apply your inverse of response matrix on your measured distribution, and then you apply some regularization term, and then what you try to get your unfolded distribution. So if you do this properly, what happened, your unfolded distribution and the true distribution should be same. So this is what is showing, done here, right? So the top panel, if you see here, these open circles are the true distribution, these true distributions. And these lines, what we call gamma light, this is like our measured distribution. And then what we do, we apply the inverse of the response matrix with some regularization on this measured distribution. And then we get back the true distribution, which is called the unfolded distribution, shown by this solid red circle. And the bottom panel, we took the ratio to see how close it is. So one can see it's like within 10%, we can reproduce the unfolded reproduce the true distribution using this Monte Carlo simulation. So this is like a closure test, and in this closure test, we also have to parameterize or like tune this parameter, these different regularization terms, or also the beta terms. So let me show you one example of how we can parameterize, or how do we parameterize using this beta and this regularization terms. So as you can see, for this multiplicity distribution, distributions have something like an exponential shape. So we use this logarithmic type of regularization here, and here we have 3 different type of weight factor. The beta value, which is very small. If we use very small value of beta, one can see there is very kind of oscillation here, which is called under regularization. If we use very large value of beta, about 10 to the power 7, one can see the unfolded somewhat different here, right? So this blue is the true, the red is the unfolded. But somewhere around beta equal to 1000, we see that we can very clearly, we can reproduce our result. So in simulation, what we do, we actually fix our parameters. For example, this logarithmic, yeah.
Can you please finish within 5 minutes, because
okay.
This is just request. You
okay,
just try, huh?
Yeah. Okay. Sure.
Okay.
Yeah. I'll try. Yeah. I'll try to finish it.
Thank you.
Yeah. So in this simulation, we play with this different kind of regularizations and this with appropriate weight factor, and we try to optimize it, and then we apply this on our real data. Okay. So there are also other methods of unfolding. For example, what's called the Bayesian method. I don't think I have enough time to go through this Bayesian method, but I'll just quickly tell you about this thing. Is that so? We all know about this Bayes theorem, where this a probability, for example, the probability of event A when the B is true, and the probability of event B when A is true can be connected by this relation. So using this Bayes theorem, one can also do unfolding, and here we have and one can start this unfolding with what is called a prior distribution or a guess distribution. One can start with some kind of guess distribution, and one can do some iteration. There is also one parameter that is called smoothing parameter that acts like a regularization, and one can also do the unfolding. So let me show you one example how it can be done using this Bayesian method. So you can see here in this figure, this open circles somewhere here is the true distribution we have in our simulation. The lines here are the gamma-like distribution, or what we call our measure distribution. Then we apply this Bayesian method. So in Bayesian method, we have what we can vary is we have the several iteration, and we also apply some smoothing parameter. So if we do that, one can see after one iteration, we get these black markers. When the iteration, we increase the iterations, we can see our result is converging towards a true distribution. And we can see here on this right-hand side plot, okay? So one can see the right-hand side plot, this has the ratio of the true to this unfolded distribution. So one can see as we go to the iteration about 10, we can somewhat reproduce the unfolded result, right? Within some uncertainty, for example, within 10%. Okay, so this is all about this unfolding method. So till now, what I talk about only this unfolding technique, only using this multiplicity distribution. But this unfolding method is also used in various analyses. For example, in collective flow, for example, the flow fluctuations. It's also used in jet spectral analysis, can also used in like a net charge fluctuation analysis. And I already give some links for you to go through. Okay, so a few more slides. So yeah, so I just wanted to give a very short example of unfolding using a package which is known as RuUnfold, but I don't think we don't have enough time. So what you can do, you can download this RuUnfold from this link, and you can do the tests of this matrix inversions and others that I talked about, and you can see for yourself. And I also list here some of the references that you can go through for this unfolding method, like different examples, different methods. Yeah. Yeah, so I would like to end here, and if you have any quick questions, I can address them.
Okay, thank you, Subhash. So I saw that there were some questions during your talk as well. And if there is any quick question, we can take one. Or maybe tomorrow, Subhash will have another lecture. Or you can also send email to Subhash or Siddharth. So
yeah, if you have any question, you can send me email, and this so these things within 30 minutes is not easy to cover everything. So I tried to cover as much as possible.
It was nice. Okay, Subhash. So
yes, Haikat. So just since this unfolding method is directly related to our PMD analysis, and a couple of students are involved, so maybe they can ask questions to Subhash, or they can be in touch with Subhash, because this is important. Okay.